Okay, so hi everyone, Senan this side, and in this video we are going to solve this surrounded regions question in on LeetCode. So the question is extremely good to think for a bit, but it's easy. Once you know the solution, it's really easy. So you are given an M cross N matrix board containing the letters X or O. Capture regions that are surrounded. Connect a cell is connected to adjacent cells horizontally or vertically. So this is for telling you that there are no diagonal connections. To form a region, connect every zeros or O's cell. Surround the region. The region is surrounded with X cells if you can connect the region with X cells and none of the region cells are on the edge of the board. A surrounded region is captured by replacing all zeros with X's in the input matrix board. Look at this example. So what is happening is you see these zeros, right? Or O's, let's say, and you have a surrounding X, this, and this. So since these three O's are surrounded, you have to fill it with X, and since this O is on the edge, so there is no surrounding X below this, so this is not a part of a surrounded region. So what I have to do is basically find a region inside this matrix such that these are bounded by X, and I have to fill those elements with X. Now if you phrase the question like this, it would be confusing. So what we do is let's frame it in a different way. If for some reason a region is somehow connected with the edge, so in that case that could not be possible, it could not be a possible solution, right? Let's consider this X as 0 as well, right? You assume this is also 0, so these 5 would be connected, but in that case we would not add X's to this zeros because this part, the below part, is not surrounded, so we leave all these 5 elements as it is. So you see a board of IG's X or O length, and this is fine. So now I showed you this because this is important for the next discussion. Now I would rephrase the question and I would say that rather than finding the surrounded islands, the islands basically islands made of O's which are actually surrounded by X, what I want you to is find all the elements that are connected with the edge and don't mark them as X's. That is the question. So what you do is find all the O's on the edge and find all the O's that are connected with those O's on the edge such that they are not, so they are basically connected with the edge, so they are part of the same island. I am just calling these as islands, but so in this case if we see there is only a single O on the edge, which is this one, and then what would happen is I find all the connected neighbors nodes which are connected with this. So up, left, and right all are X's, so there are no more O's connected to this, so we are done with this, and we say that we won't mark this as an X, and remaining O's I would mark as. So the O's which are marked as not to be covered with X, I would leave them, and the remaining O I would cover X. That is what I'm trying to do. Now if you must have observed till now we are using some breadth first search or depth first search in the solution because this is a graph problem, right? To find the number of islands, find the connected islands, it's a graph problem. It's given to you in a matrix, but it's a graph problem. So this node O has 3 neighbors, this X, and this X, because we can only go to adjacent cells which are horizontally or vertically, up, down, left, or right. So what I would do is I would use boundary DFS. This is the term used, boundary DFS. What I would do is I would go throughout these edges, and if I find an O, I do a DFS traversal from that O and find all the elements that are connected with it, and I would say that don't mark them as an X. So this is a notation that I would be using. So how do I tell the computer that don't mark this as X? I would change this O with a dummy character. So let's look at the solution of how I implemented it. So I take this M and N, the rows and columns. I take DR and DC to just travel up, down, left, and right. These are just some helper vectors. Now what I do is if I say I am this is what I equal to 0, I less than M. So I'm traveling in this first row and the last row, this and this row, and I say if I find a 0 or O in this, you do the DFS traverse. If I find a O in this, you do the DFS traverse. And in this for loop, I'm saying if you find an O in this, do a DFS traversal. If you find an O in this, do a DFS traversal. Okay, so when we are done with it, so what this DFS will do is all the O's which are connected with the edges would be marked with an hash that we'll see in this DFS function declaration later on. And now what I would do is I go I iterate over all the elements in this matrix and I say if it is hash, that means we don't have to mark this as an X. So I would say again reset this value to O. Otherwise, if this value is O, and that is only when the case that this O could have been surrounded with some group of X's, right? So in that case, I would mark them as X. So this is the whole logic. Since we are using, in this case, I would be using depth first search and that too the recursive version. So I get the M and N, the rows and columns. And since I would call this only when I see an O, I would mark that as an hash because I'm saying that this is connected with the boundary. Now I pass this delta row and delta column as a reference so that I can traverse. So row plus delta row, column plus delta column is the new row and the new column. Now I check if this is within the matrix, and if yes, is it an O? If yes, then call again this DFS because this O would also be connected with this O, this main O, the caller O. And I do this until the time I actually get I cover all the elements which are, I would basically mark all the O's which are connected with the edge by hash. If for some reason an O is not selected or O is not converted into this hash, that means that could be covered with a boundary, right? So I don't change that. And after doing this DFS, I just, as I told you, I just reverse this and in the end just return from the function. Since this is a void function, right? This is a void, so we have to do everything in place. And you could definitely use a visited array, right, to keep track of all the locations which are with the edges, and you can just compare these two matrices and find if it is not visited and the matrix has an O, mark that as an X. But rather than having two matrices, I am just not interested in that. I'm just doing everything in place. I don't need a visited array because I am able to track those elements in this original board as it is, because I know for sure the element is X or O. That is the only reason I'm able to track of the visited ness basically of the node. So that is all for this video. Let's discuss the time and space complexity. So the time and space complexity of DFS would be what? This would be about order of n square because it is DFS call is basically of order v plus 2 times e, because this could be treated as an undirected graph. So v plus 2 times of e. So v is number of vertices of the nodes. So in this case we have n square nodes. How many edges? Somewhere about n square times 4 edges, right? Because every node has 4 edges, so n square times 4, so it would be somewhere about the order 5n square. That is basically n square. What is the space complexity? Space complexity for DFS is again big O of n square, because space complexity is basically the number of nodes, right? How much depth can you go? So in the maximum depth you can go is basically pushing all the elements right into the stack. So again, the time space complexity is both order of n square, and we are not considering a visited array, so we are saving on space in that. This is a constant vector, so I don't consider this as a part of my space complex because this is fixed, just 8 integers. And yep, that is the video all about. Hope you enjoyed this, and if you did, you can share this video with someone who you think this video might be useful to. And yeah, thanks for watching and bye.